Thank you very much for the introduction. So today I'm continuing the lecture on singularities for nonlinear elliptic equations, but instead of considering with singular potentials, I will tell you what happens if we have gradient-dependent low-order terms. So again, the research is supported by the Australian Research Council. So I'll give you an introduction related closely to the problem at hand and the result, the background, and then main results and a sketch of the proofs. All right, so let's see what is the problem for today. So we will study the behavior near zero for all non-negative solutions of the problem 1. So we have Laplacian of u in the left-hand side, and in the right-hand side, we have the product between a power of u and the power of the gradient. The q is greater than or equal to 0. The power m of the gradient is strictly positive and strictly less than 2. And in order to be outside of Serin's framework, we will need to impose m plus q greater strictly than 1. Otherwise, it has been done. So this omega, as before, is an open set in Rn that contains the origin. And we are studying the equation in omega punctured at 0, removed 0, and the solutions are understood in the sense of distributions. And what do you like to understand? The solutions are non-negative, and in fact, the strong maximum principle holds as yesterday. So if we take solutions which are not identically 0, then they will be positive. Non-negative solution not identical 0 will be positive in omega minus 0. So the aim is to understand, to classify completely the behavior of any positive or non-negative solution of problem 1, the behavior at 0, at infinity, and as well as study existence and the characterization, the structure of all positive solutions when omega is Rn. So the global solutions under the assumption 2. So q is greater than or equal to 0, m between 0 and 2, and m plus q is greater than 1. So the solution, subsolution, supersolution, what do we mean? A non-negative function, which is assumed to be C1, always on the punctured domain, omega minus 0, and satisfies the equation in the sense of distributions, the test functions being C1 with compact support on omega minus 0. And of course, if we talk about subsolutions or supersolution, we have to put the right inequalities and to consider non-negative test functions. Okay, so a little bit about the background, strictly relevant to the problem, since yesterday we presented more general other results. So let's see what happens if we take m between 0 and 1, and q between 0 and 1 minus m, including 1 minus m. So in other words, q plus m is less than or equal to 1. So that forces m to be between 0 and 1 when q is positive. And we have then that Serin's results from Acta Mathematica 1965 apply. So if we have a solution in our sense non-negative, so it's bounded from below by 0, then either you can be defined at 0 and the resulting function is a continuous solution, that is in fact the distribution solution in the entire omega, or we have a weak singularity at 0, meaning that we can compare u with the fundamental solution of the Laplacian. Here, another paper, another notation. So E is here the notation, capital E is the notation for the fundamental solution of the Laplacian, that just to keep the notation in the paper. And so comparable with it, with the fundamental solution, means that the ratio between U and E is bounded from above and below by positive constants. So this is the framework in which if q plus m therefore is less than or equal to 1, it's nothing to be done because Serin has done it. More general framework, including this one. If m is now, if we take now q equals 0, so we don't have a power of u in the right-hand side, we have just the power of the gradient. So we have modulus gradient u to the m, with m between 1 and 2. Then, by the paper of Fouque and Veron in 2012 in Journal of Functional Analysis, we know what happens according to whether m is less than n over n minus 1 or m is greater than or equal to n over n minus 1. So if m is, so n over n minus 1 is exponent, that critical exponent. So if m is between 1 and n over n minus 1, for n greater than or equal to 2, then there exist positive solutions which have a weak singularity at 0. And if m is otherwise greater than or equal to n over n minus 1 for and less than 2, for n greater or equal than 3, then by theorem A2 in the paper, we have that any positive C2 solution on omega, closure of omega except at 0, for our problem with which becomes Laplacian of is equal to modulus gradient u to the m in omega minus 0, any positive solution remains bounded and it can be extended as a solution of the same equation in omega. So this is if we have the gradient, the power of the gradient on the right hand side with the power between 1 and 2 and no u to the q. Now, I'll briefly remind what happens if m equals 0 and q greater than 1. So we have the trichotomy when q is less than n over n minus 2, the critical power n over n minus 2. Q is between 1 and n over n minus 2. Then we have, by Veron's paper in 1981, we have the trichotomy. 0 is removable singularity, one possibility. The second u has a weak singularity at 0. So limit of u over fundamental solution is a positive number. And the solution can be extended in the sense of distribution with the right-hand side nu equal times the Dirac mass at 0. And the third possibility, u has a strong singularity at 0, and in that case behaves like a power function, positive constant denoted here by lambda 0 times modulus x to minus var theta 0, and var theta 0 is 2 over q minus 1. So we've seen that yesterday. And if q is above this or equal to n over n minus 2, then we know that 0 is a removable singularity for all solutions, for all non-negative solutions. And so any positive solution can be extended in omega minus 0, can be extended as a classical solution in entire omega. So that's the result of Bresis and Veron. So this is when m is 0 and q greater than 1. All right. So now what we looked at together with my former PhD student, Joshua Ching, we looked at what happens to complete the picture for m, q plus m greater than 1 and m between 0 and 2, what was not done. And so let's look at, so we have two figures here. In the left side, we have the case when n is greater than or equal to 3. And you see three different regions, yellow, orange, and blue. And the second picture on the right side, it corresponds to n equal 2, when you remember that then the critical exponent is infinity. So it's we have only two regions. So I'm going to look at the left side. So the left side where n is greater than or equal to 3, the region that is here marked in, well, green or yellow, region A. In region A, when you have q plus m less than or equal to 1, this corresponds to the Cernise result, which I mentioned earlier. And so we have either removable or solutions comparable with the fundamental solution. So that was done. If we look now at the orange region, what we do is establish a trichotomy result, removability or weak singularities or strong singularities, by generalizing Veron's result, which was in the case when m is 0 and q between 1 on n over n minus 2. So this is on the axis. On the q-axis was known when q is between 1 and n over n minus 2. And for m equals 0, and the other one for q equals 0 and m on the m-axis. If you now look at the m-axis, what was known is when m is between 1 and n over n minus 1. That was Fouque and Veron's result. And then what was left is everything in between in the region outside of the axis, the orange region B. That's what we did to complete the picture, to see that, yes, we have a trichotomy also in everything in between in the orange region. And in the region here in blue, also what was known before corresponds to the portions in blue on either on the axis, on the q-axis, when q is greater than or equal to n over n minus 2 and m is 0, the removability result that was done by Bresis and Veron, or on the m-axis with m between when q is 0 and m is between n over n minus 1 and 2. And the rest of the blue region is what we completed. So we just wanted to complete the picture when m is less than 2 and outside of the known cases. And similarly, if you look in the right-hand side, when n equal 2 was known again in region A, including the boundary when q plus m equal 1, and also on the axis only on the q axis and on the m axis. Let me then describe what were our main results. So the main results will concern existence. First, we wanted to understand whether we can have solutions in a boundary domain where you put a Dirichlet boundary condition u equal h, denoted here u equal h on the boundary. And then, of course, we did some condition at the origin, and that's where we will need to understand the classification of solutions to see what is a good condition at 0. And the condition at 0, of course, will be comparable. We need to compare u with the fundamental solution, and we take the limit as x goes to 0 of this ratio, denote that limit as capital gamma, and can be either 0 corresponding to removable singularities, or positive and finite corresponding to solutions with weak singularity, or capital lambda being infinity corresponding to strong singularities. So we wanted to confirm whether we have such solutions on a bounded domain with one boundary imposing conditions in 5 near 0, corresponding to all the types of solutions we wanted to prove that given by the classification, and u equal h on the boundary. So indeed, we confirm that assuming the condition 2 is just that m plus q is greater than 1, q is greater than or equal to 0, and m is between 1 and 2. That is always made in this from now on. And the three behaviors, so in order to have solutions, we need to have q subcritical. And in here, the critical coefficient will generalize what we knew when m was 0. Remember that the critical exponent was n over n minus 2 when m is 0. Here, the critical exponent will have also to be influenced by m. And so the existence of solutions with weak or strong singularities can only happen precisely if and only if q is strictly less than q star. And the critical exponent now becomes n, as smaller than what was before. When m is positive, the critical exponent becomes smaller, is n minus m times n minus 1 divided by n minus 2. This is if n is greater than or equal to 3. And if n is 2, then the critical exponent is infinity, like before. So it becomes smaller as m is larger, q star is smaller if n is greater than or equal to 3, and remains infinity if n equal 2. So assuming now that q is subcritical, we confirm indeed that we have that there exists a non-negative solution of the problem. There is a solution of the problem of our equation subject to conditions 5. So condition near 0 with the singularity either removable, weak or strong, and the Dirichlet boundary condition h. It has to be continuous on the boundary, and the boundary of omega will take is C1. Yeah, so this is the existence result that I will explain how we proved it a bit later. So now if we take particular cases when m is 0 and q is between 1 and q star, of course q star becomes, in this case, n over n minus 2. We already know that this theorem is valid and was proved by Friedman and Veron, and even for Laplace more general. And also in a more general framework here, also in 2010. But what is interesting in this theorem, a few things to notice up front, is that because we have a gradient factor, there are extra difficulties. One of the things that one should notice is that we did not say that the solution is unique. That is something that we cannot say, that the solution is unique simply because by including the gradient factor here in the right-hand side, if m happens to be between 0 and 1, greater than 0, less than 1, then we do not have, then there is a comparison principle, but there is an assumption, there is an extra condition that say that when you have the comparison of subsolution and super solution, with the super solution dominating the subsolution on the boundary of the domain, you will need that either the gradient of the solution of the subsolution or the gradient of super solution to not vanish at any point in the domain. And you see, this is a restriction that cannot be removed. And when m is between 0 and 1, therefore, because of this restriction and the fact that the function in the gradient is not Lipschitz, we know that we cannot claim uniqueness, at least when the domain is small. So that's why we do not have uniqueness mentioned there. We do have it, however, if m is greater than 1. Okay, so the new phenomena arise specifically when m is between 0 and 1 for the reason I've just mentioned. And what we do then in our theorem, we construct both the maximal and the minimal solution when we consider our equation subject to appropriate condition near 0 and on the boundary, as I explained, condition 1 and condition 5. And then we mentioned, as I mentioned, we have two things to care about. Is it the solution unique for this equation, our problem subject to conditions 1 and 5? Yes, if m is greater than or equal to 1, our solution is unique. But when m is between 0 and 1, we cannot say that the solution is unique. It's not necessarily unique. And we give examples depending on the domain, the condition, the boundary, and the value you take for capital lambda, that the condition at 0. We prove that clearly the uniqueness of the solution fails for m between 0 and 1. So that is, and as a main reason, of course, is this condition. In the comparison principle, you see the condition of the gradients that I mentioned. So how do we prove it? We are proving first, I mean, we have two existence results. One of them is theorem, but we also consider the case of domains, which are balls, open balls enter 0 radius r, with m between 0 and 1, and we proved by Le-Raychow the fixed point theorem. We studied the existence of radial solutions. But I want it's quite technical, so I want to show in this talk the details, but can be found in the paper, in this paper in Analysis and PD in 2015. But just mentioning that we also do separate for radially symmetric solutions. And what happens is that if you take, for example, h, a non-negative constant, the minimal and the maximal solutions, in this case, when m is between 0 and 1, so the solutions are radial, but do not necessarily coincide. That is the question when m is between 0 and 1. And we give examples. If capital lambda is 0 and gamma is finite and positive, for example, the maximal solution will be gamma, will be that constant you take on the boundary. And we construct, on the other hand, the minimal solution, which is a radial solution that is with the derivative strictly positive in 0r and taking the value gamma on the boundary of the ball, so on the sphere, u of r equal gamma. So that clearly we do not have uniqueness. On the other hand, for any capital gamma is positive and finite, so and assuming Q is subcritical, we construct a radial non-increasing solution in the puncture ball set at 0 radius r, which has a weak singularity at 0, with the limit u on e being capital lambda, and a Neumann boundary condition u prime of r equals 0. And finally, if you quickly want to see a solution that has a strong singularity, is clearly the one in a power form when Q is less than the critical power Q star. By a simple calculation, lambda times modulus x2 minus var theta with the var theta 2 minus m over q plus m minus 1. Observe that if m is 0, this is the coefficient, the power we've seen yesterday, denoted by capital theta, 2 over q minus 1. But now it's 2 minus m over q plus m minus 1. Lambda is this quantity there in relation 6. Then this function, this power function, is a radial solution in Rn minus 0. This is the solution with strong singularity. This entire solution in the entire space that has a strong singularity at 0. Okay, so now once we prove the existence of solutions, let's see that confirm that we are not missing any behaviors at 0. So we have theorem 2 here, which gives the classification of the local behavior near 0. So we have the following. If we are in the subcritical case, Q less than Q star, and Q is greater than, Q is greater than or equal to 0. Yeah, we have the condition Q plus M. Q plus M is greater than 1. So Q anything greater than or equal to 0. So if Q is less than or less strictly than the critical power Q star, then for any positive solution of 1, or you can say non-negative not identically 0 is going to be the same, satisfies one of the following, that at the origin U has a positive finite limit. The first case corresponds to removable singularity, and U can be extended as a continuous solution in the sense of distribution in entire omega, and is H1 log on omega, continuous on omega, and satisfies the equation in the sense of distributions, that is in relation 7. We can take the test function with compact support in omega, C1 with compact support in omega. Okay, the second possibility says that U has a weak singularity at 0, that is U divided by the fundamental solution of the Laplacian has a positive limit at 0. And then we have equation 8 in the right-hand side. We have capital lambda at the limit times the Dirac mass at 0. Equation in the sense of distribution. So we have U over the fundamental solution here converges to capital lambda. And that lambda you put it here in this right-hand side. And then the third possibility where U has a strong singularity at 0, and that means that U behaves like this U0 that we found by hand near the origin. So U behaves like U0 that we discussed earlier. And these are the three possibilities, which if you take, of course, if you take M equals 0, you will recover the classification result of Veron. If Q is greater than or equal to Q star for n greater than or equal to 3, then any positive, otherwise Q star is infinity, we can't take it for n equal to. So if Q is above or equal to Q star, then any positive solution satisfies only the alternative I, that is 0 is a removable singularity for every positive solution. So this is the classification. Again, we knew it, we've seen it yesterday, that this is Vasquez-Veron result, the removability when m equals 0. We are now extended it here. Okay, so the next aim, after we understand existence of solutions in a bounded domain and the possible behaviors, local behaviors near 0, all of them being also realized, the next goal is to understand fully the profile and the structure of all positive solutions in Rn minus 0. And as a consequence of this study, we will show that all solutions have to be radially symmetric. That's a consequence of the study. We prove that also they have to be radially symmetric. Now, here new difficulties. So if you look at applying the Kelvin transform, the standard Kelvin transform that I was saying yesterday does not really, it's not convenient to use such a Kelvin transform because you have the gradient factor in the right-hand side. We could not apply the moving plane method. So in order to prove radial symmetry, we will do it. We will prove the structure of our solutions and the radial symmetry, but we introduce a new iterative method, and I would like to give you some of the main ideas in that iterative method. So let's see now. Is it everything extends very much? Does everything hold as in the case m equals 0? Because otherwise it will just be a translation of everything we've seen in the yesterday when m is 0. No. What distinguishes our problem? When you introduce a gradient factor in the right-hand side, a clear distinction happens immediately compared to the case m0. Why? Because you can see clearly that any non-negative constant is a solution. Any non-negative constant, you have Laplacian of constant is 0, and u to the q gradient of u to the m, and m is not 0. So immediately any constant is a solution. Non-negative constant is a solution. And so as this has an important influence in terms of the behavior of the solutions when you consider it at infinity. So if you take a positive solution in Rn minus 0, we will prove that when having m is strictly greater than 0, it actually admits a limit at infinity and can be any non-negative number. It can be 0 or it can be any positive number. And we prove existence of solutions with such property, that the limit can be any positive number you want. Now, of course, this is very different compared to the case m equals 0, because let me remind you that if you consider Laplacian of u equal u to the q in Rn minus 0 with q greater than 1, we had those estimates that says that there exists a constant C depending only on n and q such that every solution u satisfies u of x less than or equal to constant modulus x2 minus 2 over q minus 1 for every x different from 0. This immediately tells you that every solution has to go to 0, to decay to 0 at infinity. So you see immediately that if the gradient is not in the right-hand side, then every solution in Rn minus 0 has to decay to 0 at infinity. And moreover, there are no positive solutions of this problem, Laplacian equal to the q, with the removable singularity at 0. And let me give you some papers, some references here. So if you take, the problem 9, and you look at, a bit more general, for q greater than 1, and Brezis proved in 1984 that there exists a unique distributional solution, LQ log in Rn, of the problem delta u equal modulus uq minus 1 u plus f in the entire space, assuming only f that is L1 log on Rn. And moreover, if f is greater than or equal to 0 almost everywhere in Rn, then u is also greater than or equal to 0 almost everywhere. This, the existence part was extended to the P Laplace operator by Bocardo, Gallue, Vasquez in 1993 for q greater than p minus 1 and p greater than 1, and p greater than 2 minus 1 on n. And the uniqueness issue of Brezis' paper was has been investigated by D'Ambrosio, Farina, Mitidieri, Serin in 2013. Okay, so now, as a quick reminder, this was, I reminded you yesterday. So if you take q between 1 and n over n minus, so if we are taking Laplacian of u equal u to the q, and q is between 1 and n over n minus 2, then either u is the power function, lambda 0, modulus x minus var theta 0, or is a radial solution with a weak singularity at 0 and decaying to 0 to infinity at decaying to 0 at infinity. And then for every lambda positive and finite, you can find the unique positive radial solution which behaves like the fundamental solution of the Laplacian. U over E converges to this capital lambda. And if Q is supercritical, greater or equal than n over n minus 2, then there are no positive solutions of problem 9, the non-existence in Rn, yes, for the u, delta u equal u to the q. But now, if we compare to this problem, delta u equal u to the q, the structure of solutions in Rn minus 0 is more complex, more involved. Indeed, we proved that there exist non-constant positive solutions if and only if q is subcritical, and in this case, they must be radial. All the solutions, when Q is subcritical, all the solutions in the Rn minus 0 must be radial, must be non-increasing, and satisfy relation 10. That is, U divided by the fundamental solution will have to converge to capital lambda, with lambda positive, potentially infinity. When take infinity corresponds to the solutions with a strong singularity. And at infinity, the limit of U exists and can be any real number that is non-negative, greater than or equal to 0. And in addition, all solutions which have a strong singularity at 0 are given by, well, if you take gamma equals 0 in relation 10, there is only one solution in the entire space with a strong singularity, is the one that we call it U0 in the power form. And the others that correspond to gamma being positive will be of this form, U index C, CU1 times C2, that is the transformation, C1 over var theta, modulus of x for x in Rn minus 0. C is arbitrary, and U1 denotes the unique positive radial solution in which you take gamma equal 1 in the right-hand side. And of course, strong singularity means that capital lambda here is infinity. And U index C behaves like U, like this strong singularity power form near 0, and at infinity has limit gamma. So you see that we have extra solutions because of this behavior at infinity. With the limit of U can be, it is gamma. Gamma can be any non-negative number. Okay, so then we confirm this aspect in the theorem 3, the existence and classification. So what we have, again, if Q is subcritical, for any lambda that is positive or potential infinity, and for any gamma non-negative constant, there exists a unique positive radial solutions in Rn minus 0, this time in Rn minus 0, which satisfies this condition 10 at 0 and at infinity. And if U is a non-constant solution, when then Q must be less than Q star. We remember that any non-constant, non-negative constant, any non-negative constant is a solution by default. But if you have a non-constant solution, you immediately must conclude that Q has to be subcritical, and moreover, U is radial, is non-increasing, and satisfies condition 10 for some capital lambda positive and less than or equal to infinity, and gamma non-negative constant. And by the classification, we know that if lambda is infinite, you have a strong singularity, and we discussed the behavior. And if finally you have that 0 is a removable singularity, then U must be constant. So in particular, if Q is greater than or equal to the critical exponent, and n is greater than or equal to 3, because Q star, remember, is infinity if n is 2, then U is constant. So this is a Liouville type result, the last one, that corresponds to solutions with the removable singularity, and Q greater than or equal to Q star. Okay, so this Liouville type theorems, which is relevant to the last point, have received lots of attention, and for a broad class of quasi-linear elliptic equations with the non-homogeneous term depending strongly on the gradient of the solution, here I give a reference. Farina and Serin in 2011 established that any C1 on Rn solution must be constant. But what is to be noticed here that it requires C1 on the entire Rn, not just on Rn minus 0. That's something to keep in mind. And what is good, that what's really nice is that the results apply for solutions with unrestricted in sign. And if you are restricting the framework to include M, to take M only up to 1, and so if you take Q positive M between 0 and 1, and Q plus M greater than 1, then, so here is M less than 1, then the constant functions are the only non-negative entire solutions. This was proved by Filippucci in 2009. And furthermore, Farina and Serin in 2011, they weakened the condition to allow from what was M less than 1 here. In Filippucci's paper, they extended it to M less than N over N minus 1. But what we do, we are actually improving further the result, this Liouville result, with a completely different technique. We are proving that you actually don't need this condition, M less than N over N minus 1. You can go up to M less than 2. And our proof is actually short and elementary and does not involve the test function method that is usually employed when in the literature. So it's a different method that we use to prove our Liouville result, extending in this way the range to M less than 2. So we use local estimates and the comparison principle, and I will show you how we were able to do it. So that now I'm giving some ideas. So the first proof for the 3i. So the 3i is the existence of solutions in the Rn minus 0 when you take the condition at 0 with the removable or, not removable, weak singularity or strong singularity. You don't have with the removable singularity here. So it has to be, this capital lambda has to be strictly greater than 0. And so this condition 10. So how do we do that? So the proof of this existence of solutions in Rn minus 0 relies on the radial maximal solution that we constructed on bounded domains. We take the bounded domain in theorem 1 to be the ball centered at 0 radius k. We take the boundary on the boundary of the ball, on the sphere radius k, we take the value of h to be constant gamma. This is gamma is the limit you want to get at infinity. And then when the capital lambda is you want to get, you want U over the fundamental solution to converge to lambda, capital lambda at 0, then we show that as k goes to infinity, the solution on the ball centered at 0 radius k converges to a positive radius solution with the behaviors you want in relation 10 at 0, and at infinity will converge to gamma. And And then once you do that for any capital lambda finite and positive, it's not difficult to get the existence of the radial solution when capital lambda is infinity, the solution with the strong singularity. You simply take the solution, you just take the limit, you take capital lambda to be j, and for each j and this gamma fixed, you already know that you have uj gamma, the solution, the radial solution in Rn minus 0, and then uj gamma as j goes to infinity will converge to a solution with a strong singularity at 0. And then the uniqueness follows by the comparison principle, because you will have the same behavior of two solutions near 0. The limit u1 on u2 will be 1. And at infinity, if they converge to the same constant, the difference will converge to 0. So that is when you have solutions with satisfying the same condition 10, the same asymptotic behavior at 0, and the same asymptotic behavior at infinity, then the ratio at 0 converges to 1, and at infinity, the difference converges to 0. And with this and the comparison principle, we can prove that the solutions have to coincide by the comparison principle. So that's kind of roughly how you get the solutions in the entire space. When omega is in the entire space, you get it from the existence of solutions on bounded domains, increasing the radius of the ball, and on the sphere of radius k, you take gamma, the constant that you want to get the limit at infinity for your solution. So that is the idea. Okay, now several tools that we need. Some I would like in the rest of the time to show you a few of the tools and novelties compared to the case what appears new when you take the gradient. Okay, so the first thing to observe is the comparison principle, that we need to be very careful. So the one that we are using here, this theorem 10.1 in Pucci-Serrin's book. So we have that omega is a bounded domain, and we have this nonlinearity, the lower order term b, depending on xz and the xi. The xi will be for the gradient, z will be for the solution u and x, the space variable, which is continuous in omega times r times rn, continuously. See, this is the continuously differentiable respect to psi for modulo psi greater than 0, which is satisfied. Assume that b hat, the nonlinearity is non-decreasing in z, also is satisfied for us for fixed x and xi in omega times rn. And if u1 is a subsolution and u2 is a super solution for problem 11, so you have u1 subsolution, u2 super solution, and u1 dominated by u2 on the boundary, in order to deduce that the inequality extends in omega, you need the assumption that the sum of the gradients of u1 and u2 is strictly positive. And now this is a restriction that is mentioned in Pucci-Serrin's book. You cannot really remove it. If you remove it, you get counterexamples. So, so the lesson here is that in practice, what you will be using, you will always take one of this, either solution or super solution, to be a solution of your problem, and the other one will be your sub-solution or super solution that you do by, you choose. So in practice, only because your solution will be arbitrary, with the solution you can't do anything. You can't assume that the gradient does not vanish. So then is a very big restriction. Always you have to check that your super solution or sub-solution doesn't, the gradient of that does not vanish, and that can create difficulties. But the version that if we allow now there is another version that we also use, is the following version. So now we assume that b hat, you have better conditions. B hat is locally Lipschitz continuous with respect to psi, and is non-decreasing in z. So what we allow here, locally you have a bit more. You have locally Lipschitz continuous with respect to psi. And then if u1 and u2 are distribution solutions in w1 infinity lock on omega, for the problem that I showed earlier, for this problem, then if u1 is less than or equal to u2 plus m on the boundary for some positive constant, you extend it in entire omega. So what is here, when do we apply this comparison principle? You can apply it only when m is greater than or equal to 1, because then our right-hand side, u to the q modulus gradient u to the m, will satisfy that this local Lipschitz continuous. But if m is between 0 and 1, unfortunately, we cannot apply lemma 5, and we have to go to lemma 4, and we have that restriction of the gradient. That's always have to be kept in mind, this kind of restriction. Now, I mentioned quickly that the strong maximum principle holds simply because in the sense that if you have a non-negative solution that vanishes at some point in the domain omega minus 0, then the solution has to be identically 0 in omega. And here simply you apply Young's inequality on the right-hand side. You apply Young's inequality. You take P greater than maximum 1 on Q and 1, and MP prime greater than 1. You can find P. You take P with such a property. P prime is the Hölder conjugate of P. You apply Young's inequality, and then you have you can apply the theorem 2.51 in Pucci-Serrin. So you can apply the comparison. You can apply the strong maximum principle in Pucci-Serrin. So it's not difficult to prove that the strong maximum principle holds. Now, a priori estimates, again, this is something that is different from the case when M is 0. What is different here? So what is different is the following. We cannot claim that, so let me say, so you have R0 and you have the closed ball centered at 0 and radius to R0 included in omega. And you have a solution or a sub-solution for your problem. You can find a constancy one which depends on the parameters M and Q, and C2, however, another constancy 2 which depends on R0 and U, such that inequality 12 holds. So now you have U of x less than or equal to C1 modulus x2 minus phi theta. What we had yesterday, basically, with adapted power, with the new power from the strong singularity, but you have to have plus C2. C2 depends this time on the radius and the solution U. For modulus x between 0 and 2R0, and for example, C1, you can take this constant for the C1. You see, depends only on the parameters of the problem, but C2 depends. You have to, in order for this to work, you have to take the maximum U on the sphere. And let me just quickly say, why we cannot get rid of C2? Well, I already mentioned that the fact that you have the gradient, simply you can visualize that any non-negative solution, any non-negative constant is a solution. So therefore, you cannot cut the C2. You cannot really remove the C2. It's clear. You have to have a constant C2. So that is the difference here compared to the global estimates that we've seen in the case when M is 0. So the method of proof here is different. The super solution that we construct is now on analysis. You have to go away from 0, because at 0 you don't know anything about an arbitrary solution. So we go away from the origin. We work on an analysis with the modulus of x greater than delta and less than 2R0, and the super solution you see that it blows up on the sphere of radius delta. That is the important point. And we also have to make sure that the super solution F delta dominates the solution U. So the C2 will help us to, by taking C2 the maximum of U on the sphere of radius to R0, we guarantee that F delta dominates U on the sphere of radius to R0. And obviously to dominate also on modulus x equals delta. And so also, we can see that this gradient of F delta is not 0 in the analysis A delta, and so we are free to use the second comparison principle, the one with no restriction. And so, the first one, because the gradient is different from 0, the first comparison principle, and then we can extend the inequality from the boundary to the entire A delta. And then simply you take delta going to 0, and that will give us the inequality we want. So the proof is not difficult, but it already shows that we need a constant C2. Okay, so now without proof, mentioning a few tools that are very, very important in the paper. One of them is this lemma. I don't know why the number goes to 1 and was not in the increasing order. So the first is that if you have a positive solution, and important here is that is in Rn minus 0. The solution is in Rn minus 0. Then it's very important that when you fix a delta, or any delta positive, and if you look to the right with the modulus of x to the right of this delta, then the values of U decrease with respect to the maximum of U on the sphere of radius delta. That is a very important result that we use quite a lot. So U of x is less than or equal to the maximum of U on the sphere of radius delta when you go with the modulus of x to the right of delta. This is important. Then, as a corollary of this result, from the proof of it, you can see quite, but I don't give the proof, but from the proof, you see that any positive C1 Rn solution in Rn will have to be constant. So with removable singularity here, this is C1 on Rn. And if you take a more restrictive range, as mentioned earlier, this corollary too was proved by Farina and Serin, but under more restrictive conditions. This result I mentioned yesterday, even more general, and is true here as well. So if you have a priori bounds of the solution, then you get gradient estimates, and in the form of 16, you can actually replace, you can just say, yeah, this is a particular form of the upper bound that is relevant for our profiles. That's what, so with the maximum rate here is modulus x2 minus capital var theta and zeta equals 0. But you can really do it a bit more general to say that there exists a constant C alpha such that for any x and x prime with this modulus of x and x prime less than R0, you can actually put U instead of G in relation 16. But anyway, this with a similar proof. You need to prove, however, before that, a spherical Hanna type inequality, like I mentioned yesterday. This constant here, however, depends on R0. Depends on R0, at least the way we made the proof. And the first alternative in the classification was that if U is dominated by the fundamental solution then of the Laplacian, then we have that 0 is removable singularity. This is a actually very short proof. So how we do it, because U is dominated by the fundamental solution by a simple comparison principle, U is dominated by, for any epsilon, and you find a constant C such that U is dominated by epsilon, the fundamental solution plus a constant, take epsilon to 0. The constant, choose it to large enough to dominate the U on some sphere of radius R0, where you, on the boundary of the ball where you compare, and immediately get that the limit superior is finite. And then with that information and with the gradient estimates that I showed earlier, you look at, that I mentioned earlier, you see that the right-hand side, modulus gradient U to the M, U to the Q, is going to be dominated by C1 modulus X to minus M, times something U plus C2. So, and then we are in the framework of Serin, because M is less than 2, and by Serin's result of removability, U can be extended as a continuous solution in the entire domain. So this is essentially, this is not long at all, observing that we can, by the fact that U has finite limit, you can apply Serin's removability result. But now why the limit is positive? This is a technique that I will use a bit later as well. So what the idea is the following. We know the moment that the limit exists is right, and that is finite, but we don't know yet that is positive. So how do we prove it? The idea is to get to convert, to relate our problem, to create some auxiliary problems, or an auxiliary problem, which is problem 22, in which you get rid of the gradient. So that means you have to look at the right-hand side of your equation, and using the gradient estimates, get rid of the gradient, saying that the gradient of U, modulus of gradient U, less than a constant U over modulus of X. And we do that in this inequality 19. And that's very good, because now it tells me that U is a super solution for a problem that doesn't have gradient. And notice now that the power of W, the power is M plus Q, which is greater than 1. So basically working, we have, again, in order to make sure that you can have the right condition here, you have to work first on annually BR0 minus a sphere ball centered at 0 radius 1 on K, and take the W, we create this auxiliary problem 20, where you take the minimum of U on this boundary of this annulus of radius R0, the larger one, and 1 on K, the smaller one. And then that ensures that this WK, you know, this problem from what we discussed yesterday has a unique solution, is radially symmetric by uniqueness and by the symmetry of the problem, and it's increasing in K and is dominated by U, because U is a super solution by relation 19. So what we've done with this, we are now creating, by taking the limit as K goes to infinity, we create a solution for a problem which has a removable singularity at 0 and has no gradient in it. and has the power of the unknown n plus q greater than 1, and here is modulus x to minus m, exactly what we discussed yesterday. And for this problem, it's known that the limit of u is positive. And if you want even more general, it's in my my paper how to prove that the limit is positive, in more general context. So therefore, because w is below u, that ensures that the limit of u is positive. So that's a very useful tool, creating an auxiliary problem that you have, which does not have the gradient, for which you already know the classification, you know everything. That was really the idea. And then the Liouville result. Let me see how we prove this Liouville result. The very, very short proof once you have that lemma 1. So if we have a solution in non-negative solution in Rn minus 0, and 0 is a removable singularity for you, we know already that this should only happen, can only happen when q is greater than or equal to q star, then u is a non-negative constant. So already from the result that I have just shown, because we have a removable singularity case, we know that the solution will have to be extended as a continuous solution in the sense of distributions in Rn. And then all we need to do is to prove that u0 equals to the limit superior of u at infinity. Once we prove that, we are done. Let's see why. We know already that if you look for fixed delta and you look at the maximum of u on the sphere of radius delta, that maximum is going to dominate all the values of u when you take the modulus of x to the right of delta, modulus x greater than delta. This means that the supremum of u on Rn happens, it's u of 0. That is the fact that we are using. That is the lemma 1. This is that the fact that as you increase, as you go to the right, the values of u decrease with respect to the maximum spheres that are to the left. And so u is less than or equal to u of 0. And now if you have a point z different from 0, such that u of z happens to be exactly u of 0, in view of relation 23, that will mean that you will have to be u of 0 in Rn. And if you were not to have any such z, then you get simply, you get a contradiction, because by the property in lemma 1, we know that as you go with the modulus z to the right of 1, the values of u have to be less than the maximum of u on the sphere of radius 1. And the maximum of u on the sphere is less than u of 0, strictly, because there is no z such that u of z is u of 0. And so you get the u of z must be less strictly than u of 0 for all modulus z greater than 1. And that's a contradiction to relation 23. So all we need to do is to prove relation 23, that the limit superior at infinity is u of 0, which represents the supremum of u. So how do you prove that? By the comparison principle. So if you look, so fix x epsilon arbitrary, and if you take large enough radius r epsilon and you take modulus x above that, greater than or equal to r epsilon, obviously you will have that u of x is less than or equal to the limit superior of the infinity of the limit superior of u at infinity plus epsilon. This is clear. And now we need to see what happens near 0. Near 0, of course, we will be taking in relation to the fundamental solution. So if you are with n greater than or equal to 3, take epsilon times the fundamental solution, the constant epsilon modulus x to minus n. And if you are with n equal to, we have to be a bit more careful because of the log factor. We have log of, and we put this r epsilon divided by modulus of x in front 1 over r epsilon. And since u has a removable singularity, u on fundamental solution goes to 0, it means that if you are very close to the origin, u is dominated by such f epsilon. Okay, that's clear from the u divided by e goes to 0. And then all we need to do is now we fix z in Rn minus 0, and we know already that if you are close to 0, u is dominated by phi epsilon. If you are with z large, is dominated by the lim sup of u plus epsilon. And in between, by the comparison principle, because the right-hand side here, f epsilon plus the constant, this limit superior plus epsilon, this is a super solution. You have the inequality extended for every z different from 0, for a z in Rn different from 0, and then we take epsilon go to 0. You take epsilon goes to 0, and you get that u of 0 is less than or equal to the limit superior. And that finishes the proof, because we know that u0 is the supremum of u on Rn. And so you see it's quite simple by the comparison principle, but of course relies on lemma 1, which is the critical ingredient to conclude. Okay, Now, some remarks that if you restrict to m between 0 and 1, so I must emphasize that this result works for any m less than 2. Okay, but if you are restricting m to be 0 between 0 and 1, then this was already known, and it can be proved differently. Either you can use lemma 2 or you can use show that you see 1 on the uniball and then use lemma 2, or alternatively we have that you is in H1 log, and then you can use Filippucci's result and based on a test function technique of Mitidieri and Bohozaev. So, but of course our proof is different, not only for m between 0 and 1, but extends up to m less than 2. Now for the existence, I would like to yes, I was actually quite slow. So for the proof of theorem 1, for the existence result, what I want to say, what is here different? Because we have the problem with the gradient, potentially m is between 0 and 1, and that is a big impediment for the comparison principles. Also for the existence, when you consider the problem on annuli, if the function is not C1, the gradient, or in the unknown u, then, you know, we wanted to apply the classical results in Gibbard and Schrödinger, this theorem 15.18, and we needed the function in the right hand side to be C1 in U and in the gradient. So for this reason and the comparison principles and so on, we wanted to perturb the problem. And how it is, we perturb the problem. We put all the conditions you wanted 0 on the boundary. I'm here illustrating on the ball, but to perturb the right hand side. Observe that as n goes to infinity, the right hand side becomes what you want. But to perturb it to get the smoothness you want. And then the first is to prove that for this perturbed problem, you have a unique non-negative solution. And because you don't have problems with the comparison principle, everything will work. First, you have to work on annuli, like I showed earlier, a little bit earlier with on annuli, and then take the inner radius shrinking to 0 with k larger and larger. And for this problem 25, where you take it on annulus with the appropriate boundary condition, you have to be a bit careful here to add maximum of h on the boundary in order to ensure that this lambda e plus maximum of h on the boundary represents a super solution. That's why we added this, but that doesn't harm because the fundamental solution blows up, and lambda here is a positive constant, so it doesn't harm to add the constant. Doesn't change the behavior as 0. And this is classical. This has a solution, is unique. You can prove that it's non-negative, therefore is a consequence, and also positive, and pass to the limit. Everything works because you have gradient estimates, you have monotonicity gradient estimates, pass to the limit, and then with the reduction that I showed earlier, with the comparison with the problem without the gradient, problem 28 is similar to what I showed earlier. You can get the existence for the perturbed problem, and then you take and go into infinity. Again, you have monotonicity, you have a priori bound, which is this super solution, and you can pass to the limit and you get rid of the perturbation. That's really the key. For the uniqueness, for the fact that the limit exists at infinity, it is the new idea. How many minutes do I have? I don't know if I have time to show.
You have about 2 minutes, but we can extend. I'm sure. How many minutes do you need?
Well, 2 minutes just to show a few words, say a few words.
Yes,
about it.
you have them.
These are 3 slides, but I'm only going to say a few words about that. So now the novelty, and I mentioned earlier that the somehow maybe surprising at the first sight that the limit at infinity exists, can be any non-negative number, and that the solution is radially symmetric and non-increasing. How do we prove the existence? This is something that I think it can work in other contexts. So to prove that the limit exists, first of all, we already know that the limit superior at infinity is finite. So to prove that the limit exists is essentially this claim, which I'm not proving here, just mentioning it. So what we want, the claim is the following: that if you take any sequence that increases with the modulus of x and increasing to infinity, for each epsilon, you can find n epsilon large, such that for every n greater than or equal to this n epsilon, the values of u are dominated by the limit superior of u of xn plus epsilon for every z in the ball centered at xn, with the radius modulus xn on 2. And it's going to be, so this is, imagine this xn has the radius larger and larger. But the idea is that we will iterate this by choosing, the iteration is very, very nice, because if we assume this claim, you take a sequence xn1, the first sequence, xn, comma 1, you take a sequence with the limit of u xn being the limit inferior. That's the starting point, and you apply the claim. So therefore, if you take n large enough, then n1, then you have that u of z less than limit inferior of u at infinity with plus epsilon for z in this ball, closed ball, centered at xn1, modulus xn1 on 2. Now, if you visualize this closed ball and you intersect it with a sphere of radius modulus xn1, pick one of the points on this intersection, call that xn2. So xn2 has the same modulus as xn1. And now you apply, because of this inequality, 32 applies also for xn2 instead of z. And then because of the claim, in the claim, now the limit superior of Vxn will be applied. You apply the claim for xn1, for the sequence xn, for this xn2, which has the same modulus. And so you end up with u of z less than limit inferior of u plus 2 epsilon. But now you are increasing the range of z. You increase the epsilon because you apply twice, it's epsilon plus epsilon, but now you increase the z, the range is the union of two closed balls. And as you repeat this, you can cover the sphere centered at 0 and radius xn1 by a finite in many closed balls like this. It's like when you do Harnack inequality, basically, on spheres and cover the sphere with finitely many balls. That's the same idea in terms of covering. And so you repeat finitely many times, so you get that u of z is less than limit inferior plus k epsilon with k independent of n for all z on the sphere of centered at 0 radius modulus xn1. That's perfect, right? After finitely many numbers, the sphere of radius modulus x1 is covered by the union of these balls. Modulus xn I is modulus xn1. And so then that gives you, for all modulus z greater than or equal to modulus xn1, because of the, remember what happens with the values of u, as you increase the modulus, the values decrease in respect to the supremum. And so we use that fact to conclude that the limit superior of u is less than or equal to the limit inferior of u plus k epsilon. And then you take k epsilon go to 0. So then limit superior is equal limit inferior at infinity. So that was the idea. So once you have the claim, after finitely many steps, you get a contradiction. You get the limit exists. Sorry. Well, thank you very much. That is all for today.
Thank you.
Thank you.
Colleagues, let us propose to organize some discussion. Maybe somebody has some question. Please ask. All microphone is switching on. Please ask all questions.
Yeah. Can I ask question?
Please, Lauren.
First, I would like to thank Florica for his beautiful talk, because it was very interesting. And I have a few questions. Well, first the question is about your removability result. Do you really need U to be positive? In theorem 2?
Yeah, so so what I would need is U to be non-negative.
No,
and
well,
if
non-negative,
it's not
say, because U plus is a sub-solution.
Yeah, so I haven't tried for every solution. I haven't tried. So, so I needed U non-negative.
You're sure? Because U plus is a sub-solution, no?
Yeah.
Of your equation.
I haven't looked. I haven't thought about it.
No, well, I don't think it changes.
I always start with the negative, so I wasn't really thinking.
Okay.
Thank you. I will think about this.
No, I think it is the same. I think probably. Well, do you think there is a whole interesting theory which is about the changing size solution and boundary singularity? And I think for that, the first start would be to look at a separable solution, and probably you will have a new threshold of existence of a separable solution for that.
Yeah.
Okay.
Yes, thank you very much. Yes, I will follow this too.
Yeah. Okay. Thank you. And in this direction, do you know the paper of Marcus and Gwen Shoktai? Because they have studied also this type of similar type of problem. I think it's I have only it under the form of an archive preprint.
I don't have it.
Okay, so
No,
it could
I
be
don't know the
interesting for you to see, to look at it, because they look at that, this type of problem also with that. And I remember more or less that they have similar similar threshold which appear in the construction.
See. Yes, no, I don't know the paper. Thank you.
Okay. Well, if I have time, I'm going to ask a new question.
Yes,
in
yes,
dimension 2, should be interesting to look at Laplacian of u equal exponential of u grad u to the m.
Thank you. That indeed looks very, very interesting. Yes, I love this problem. So
It could be
yes,
interesting.
that's an excellent project.
Okay. Well, I'm going to stop question because ask me.
Thank you so much. Thank you.
I will send you many questions.
Thank you.
Some of my questions. But really, what now all this business about removable point for equation of diffusion absorption. What do you mean about removability of some more complicated, not point singularity, but maybe some smooth manifold, closed manifold of dimension less than n dimension of our domain, and something to do about this direction. Is it possible or not? What do you mean? But for estimate, it is this direction. It is necessary to develop such a theory in this direction.
Yes. It is essentially here used that we are working with an isolated singularity, and basically you see we used a lot the comparison principle, and so that is how we get very nice and sometimes very short proofs. So I don't know if you are changing if you are changing the dimension and the other things on the singularity, the set of singularities, that I don't know how that, if these methods can be extended.
Yeah, I understand, but really, in fact, it is now this tool always goes to some ordinary equation and some analysis of need to radial solution. No, but it is not this old idea, old picture of analysis, but something for such non-radial situation. I mean, because it is very actual, in my opinion. Not.
Yeah. Thank you.
You are a specialist. Maybe from my point of view, it is necessary to understand how to work with such a removable singular set. No complicated. No, maybe starting from some very smooth, very some simple geometry, but it is necessary to understand what will be. Yes.
Yes, I agree. That's a very interesting topic, and indeed, in many contexts, the question of removability of singularities indeed has been addressed in more general frameworks, and of course, understanding singularities is harder. But first, to understand when you don't have singularity, when you can remove them, and I think this I've seen papers, but like more in many other frameworks. But maybe
for harmonic functions, there is such a theory of removability of different singular sets, but some analog for equation for like a diffusion absorption, general frame. Laurent, what do you mean in this direction? Maybe you
I don't know.
Have some idea.
I was thinking of something else. Don't worry.
No, yes, it is very important for me to hear the opinion about such a good specialist like you. Thank you very much, for the talk. So we don't have any time now.
There is a question. There is somebody who asked a question. Marie-Françoise is asking something.
Please. Marie, excuse me. Please, you have some question, please. Oh, switch on Microsoft.
Microphone, Marie.
Microphone is not switched.
Yes. Now you hear me?
Yes. Now it's okay.
Yes.
Okay.
Yes.
So first, your work is very interesting. except in particular when m is less than 1 because of the non-uniqueness results. I have small remarks concerning the existence of solution. You prove that they exist, but it is quite long, and you prove that they are radial. Maybe you could prove directly that the radial solution exists with by using a phase plane technique, I am sure.
Yes,
so
I haven't
maybe
tried
it would be shorter.
Yes.
I don't know, but
Okay,
it could be shorter.
Mm-hmm.
Another remark, you obtain your estimates of U, and then you deduce estimates of the gradient by,
Yes.
after that, it needs that m is less than 2. I think that you have, with Chang, used Bernstein technique to prove directly the estimate of the gradient, and then obtain the estimate of U by integration.
Yeah,
I think
that's right.
it's more powerful.
Yes, that's right. Thank you.
yes,
That's correct. Yes, that's correct. Thank you. Indeed, we had very general for P Laplacian type and more general in the right hand side. That's correct. Yes. That's a very good, excellent remark indeed. I did think indeed, and I'm doing now more complicated than this one, where with Maria Forcășanu, and we are including a potential and also a power, so more general terms. And when lambda is negative, then we could use that technique in that paper with Joshua Ching for the gradient estimates and then up to estimates. But we could not do it when you have the Hardy potential, and that's the only thing we are stuck. If lambda is positive and it's competition, the wrong sign is lambda positive, lambda the Hardy potential in the left hand side, the positive, and then the right hand side with the gradient, and we cannot apply. I don't know, we cannot do it with the Bernstein technique because they enter into competition because they have opposite sign when you go in the same equation. But when lambda is negative, when you have the right sign, there's no competition. This Bernstein technique can work even with the Hardy potential.
Yes.
So yes, that is very powerful. To get
So
in
no,
the first gradient. Thank you for the observation. It's correct. You can obtain gradient estimates first and then a priori estimates. Yeah.